Okay, welcome folks. Section 1.8, we're just going to do the front page in this little video, and then we'll probably do the rest of this in class, but we'll record that too. But just to get started, we're going to talk about inverse functions in section 1.8. This is what this is all about, is inverse functions. And just before we dive in, just a real quick informal definition. Okay, if I've got, we're going to use this definition using composite functions, but before we do that, just always keep in mind that inverse functions are to take x comma y and just transform that over to y comma x. And you've been doing inverse functions really your whole math life, anytime we add and then subtract doing inverse functions, because what we're really doing is just inverting the input and the output. Now, to start with, though, we are going to do this kind of thing if two functions are inverses. So just as a quick example, if I have f of x equals x plus 2, we have g of x. And if we want g of x to be the inverse, we already know this. Like, how do I undo addition by 2? I just subtract 2. And so those would be inverse functions, a really simple example. But if it gets more complicated, we kind of have to sometimes test to see if things are inverses. And here's what we know. Here's a little bit of a theorem for us. If you put those functions together, and if they're inverses, so this is a little bit of an if. So if you put the functions together and everything cancels out, all the operations cancel out, and you're just left with an x. Okay, and that works in both directions. So if you put f inside of g and g inside of f, okay, then what we can say is that g of x is equal to, and there's maybe a new symbol for us. We're going to do f with a little negative 1 in there, and that in words is the inverse of f. So again, what we're looking for is every operation canceling, and we're just left with our identity where we get the y equals x. Again, if you try that up here just real quick, so if I do f of g, I would get x, oops, yeah, so I'd get x minus 2 going in place of that x, and then I'd add the 2, and those 2's would cancel, and I just get x. And if I did the other way, I'd get the same thing. So that's what we're looking for on these first two examples is, does everything kind of cancel out? So let's give this a go. So on number 4 here, if I do f of g of x, that means I'm going to take f, wherever there's that input, I'm going to replace it with all of this stuff. So this looks pretty messy, but it's going to work out pretty nice. So we're going to do something like that, and then plus 9. Okay, and if I look closely, I've got a 4 up in the numerator and a 4 in the denominator. I've got multiplication signs next to those. There's nothing else down by that 4, so I can go ahead and cancel those. And that gets me x minus 9 is the only thing that's left, and then that plus 9, and so that is equal to x. I'm going to kind of double underline that, because that's what we've got. And then we're going to just switch the order. So we're going to do g of f of x. And on g of f of x, that's going to take that x, take all of f, put all of f right there. So I still have the fraction, I still have the minus 9, I still have the division by 4. I'm going to put 4x plus 9 where that x was. And if I work that out, I'm going to get 4x, but the 9's canceling out, so I have 4x divided by 4. No more addition subtraction, so I'm legally allowed to cancel those 4's now, and I've got x. Okay, because those both work, I know that f inverse is equal to g of x. Okay, so that's what the work looks like for those guys. It's a little bit tedious, but what we're just saying is those are inverse functions. Let's try number 8 real quick. So f of g of x. I'll go a little bit quicker this time, so that's to take this x, put all that stuff in there. So we're going to go 2 on top, 2 over x plus 5. Okay, so that's all the stuff from g, and then the minus 5 is still kind of hanging out. The algebra here is a little bit messier, so we'll take our time a little bit. That's a 2. If you look in the bottom, okay, I've got those parentheses, but I can do the 5 minus 5, and I'm just left with 2 over 2 over x. To clean that up, think about this as a fraction. You've got 2 over 1 on top. You've got 2 over x on the bottom. At any time you have a fraction divided by a fraction, it helps to kind of go back to 4th grade and think about how we do that. Fraction divided by fractions, we're dividing like this. The only way to do that is to flip the second one over and multiply. And if we do that, then we can see that those 2's cancel. And so I'm just left with x. Okay. Which is, again, kind of what we want if we want these things to be inverses. For the second part, when I switch the order, g of f of x. That's going to get me the g on the outside, so I'm going to leave this 2, division, the plus 5 stays, and now I'm doing 2 over x minus 5, all in place of that little x that was there. And we get that same situation. You've got a fraction here, okay, divided by another fraction. So I'm going to treat this as 2 over 1 times, I'm going to flip this over, so x minus 5 over 2. So that whole messy thing turns into this. Then the plus 5 is still there. These 2's can go away because, again, I've got no addition or subtraction next to them. Leaves me with x minus 5. And I've got x minus 5 plus 5. 5's are gone, and I've just got x. And so one more time, I've got that g of x. And make sure we kind of finish these. The instructions say to determine whether they're inverses. On both of them, they are. So we should finish by saying g of x is equal to f inverse of x. Okay, that would be our conclusion, but we got to show all that work just to justify it. Okay, and then the last thing we'll do on the video here is just, and this is something you've done in the past for sure, but we've got one-to-one functions. We'll talk about what we mean by one-to-one, but in a really short version, one-to-one means a function has an inverse, and so it's worth trying to find that inverse. And so finding an inverse looks like this. We are going to take the output and the input, and we're going to switch them. Now, this is our y, that's our x. So to find the inverse, the process is to invert that, to switch the input and the output, and then we're just going to solve that back for y. Another way to do this is to solve for x immediately and then just swap the variables when you're done, but it doesn't really matter. So some of this is pretty easy. Like this isn't bad. We add 1, we add 1. I would get x plus 1 on the left. I get a y cubed on the right. I'm just undoing all these operations. So how do I undo a cubed? I'm going to do a cube with a cubed root. So I do that to both sides. And what I'm left with is y equaling the third root of x plus 1. Once you've got that y isolated, you're done, okay, with the work. We're just going to do one more thing. We're going to say that implies. So once we know this, we know what's going to come on the right side. That arrow might be a little bit new. It's an if-then statement. If this is true, then this is true. And what is true now is that the inverse of x, or of f, is equal to the third root of x plus 1. So that's what we're looking for because our final answer, notation-wise, that's important because we have a new function. It's not the same as the original, but it's related. So they both have f, but we put the little -1 in there to say this is a different function that is derived from the original. Okay. Let's see. These can get a little bit messy when we start getting messier functions, obviously. So let's look at 28 real quick. So this is my y. And so I'm going to swap. I'm going to put the x over there isolated. We got 2y minus 3 over y plus 1. We talked about this a little bit here. It's becoming a theme, but anytime I have a variable in the denominator that I'd like to isolate, I've got to get it out of the denominator, even if it shows up in the numerator also. Let's go ahead and get this up in the numerator so I can do some work with it. So we'll clear the denominators. And that's going to get me y plus 1. And on the left side here, for the sake of just being brief as we can, we are going to need to distribute that. So let's go ahead and do it right now. So this is xy plus x. On the right side, those are gone. So I've got 2y minus 3. Okay, step back for a second, think about our goal. Our goal is to get the y variable isolated. Well, you've got 4 terms here, and 2 of those terms have the y variable that we want to isolate. So the blue terms have the y. We want to get those together and any other terms away. So we're going to gather the blue terms and gather the red terms. And so all I'm going to do is pick this 2y up and move it to the left. And I'm going to pick this x term over and move it to the right. And that'll kind of gather up all of our terms. Our like terms is essentially what we're doing. So I'm going to have xy on the left, and this 2y was positive on the right, so it becomes a negative on the left. The -3 is going to kind of stay put over here on the right, and I'm going to move this x over. Again, it was positive on the left, so it becomes negative on the right. And there we go. So now we have this new equation that's the same as that first one, equivalent equations. The goal is to get this y isolated. The reason we kind of gather them is now I can come up here, and what we can do is factor a y out. So think of the y, kind of undistribute the y. So the y is coming in front. I've got x, I've got -2, and then I've got x minus 3 over here. Negative, don't forget that negative. And I'm almost done. Okay, one more step. I've got that y. It's attached with multiplication to this x minus 2. So all I need to do to get the y isolated is divide by x minus 2, divide by x minus 2, and I have y equals negative x minus 3 divided by x minus 2. Okay. Again, one last kind of just notation step. We want to replace that y, then kind of kick it out and replace it with this inverse symbol. We have f inverse of x is equal to negative x minus 3, all divided by x minus 2. Okay, so that is that. And just one quick note. Well, let's do one more example, then we'll do that. I'm going to leave 22 to you guys, see if you can handle that. But let's check out 25 here really quick. So I've got, again, y instead of that f. I'm going to switch those. So I'm going to get x equaling 7 over y minus 3. And away we go. Now, again, the thing we want is in the denominator. So we're going to try and clear that out. We've got a couple ways we could do it, but let's just go ahead and get that 3 over the other side first. So I've got x plus 3 equals 7 over y. And then we don't really have a choice. We've got to get that y up into the numerator. So I'm going to multiply both sides by y. This is grouped on the left, so be careful. That's going to leave me with xy plus 3y equaling 7. And notice the similarities here. We're essentially the same thing as we had right there. We've got two terms, both have a y variable. So what we're going to do is undistribute that y, pull it out in front, open some parentheses, think about what was left behind on those two terms. So we have an x, we have a plus 3, the equal 7 is still just hanging over there. And then the hard part's over. So all I need to do is divide by that x plus 3. And we're going to get y equaling 7 over x plus 3. Or f inverse of x is equal to 7 over x plus 3. That's our final answer. Okay, and just quickly, like, what do we mean? Why is this important? Well, come back to the original thing and say, you know, like, what's f of 1? What is f of 1? If I put a 1 in here, 7 over 1 is 7. 7 minus 3 is 4. So I have a point on f is 1, comma 4. And the inverse, then we should have a point on the inverse at 4, comma 1. Meaning, if I do f inverse of 4, if I just switch the inputs and outputs, instead of inputting 1, I input the output on f, which is 4. If I put that in there, I get 7 over 7, which is 1. So sure enough, I have a point at 4. That's the whole idea of an inverse, is we can swap the input and output. 22 is going to be a little bit weird, so try it out using the same thing we just did, and see if you can get it. It's a lot easier, but it's just a weird result. So that's it. I'm going to stop, and we'll finish up the rest of this in class.